Most of the questions we have already done, isn't it? So we will see the remaining few questions. The remaining we have done already. And so we did the first question yesterday, isn't it? And the second one is a direct question. And the third one we did, isn't it? Copper pyrite more difficult. I think I gave you the answer. Why is extraction of copper from pyrite is. Did I give you the answer? 6.3? No, okay, write down the answer for 6.3. They are asking why is extraction of why is extraction of copper from pyrite more difficult than from the oxide ore? So what is the reason? The first I will explain. The copper pyrite is a sulfide ore and it is difficult to reduce sulfide ore. The reason I told you, anybody remembers in the class when I taught, I told you, carbon we cannot use directly from sulfide ore. Why? Or hydrogen we cannot use. Why? I told you the answer. Anybody remembers? Who is this? Accept my request. I accepted, no? Kirtana. Who is that?
Yes.
I accepted.
Yes, ma'am. I
Before
wasn't
you.
able.
Okay.
So,
Okay, tell me the answer. Vishnu Priya. Where is Anand? Ruchi, Varshini, Varsha, Varshini and all very quiet. Not at all participating. Varsha, where are you?
Ma'am, we can't remove the full amount of FES in one step.
No. I am not talking about FES. Here it is copper. Pyrite is a copper ore.
Cu2s on heating will convert into CuO and FES will react to form Cu2s.
I'm not asking the extraction. The question is, why can't we directly get copper from the sulfide by reduction? See, normally we convert it into oxide, then use a reducing agent. The question is, why can't, say Varshini. You want to say something, Varshini? Not, I'm not able to hear you. You're not audible. No, Varshini. See, the question is, why can't we directly, see, after concentration, directly, why can't we use a reducing agent? Sulfide to Cu2S to Cu directly. That is the question. So what we do convert it into oxide, isn't it? So you read the question. Why is extraction of copper from pyrite more difficult than from oxide? Oxide means directly you can convert it into copper using a reducing agent, but the sulfide directly we cannot. We have to first convert it into an oxide. When I taught you copper, I told you the answer. Anybody remembers Anand? Anand is not there. Anand.
ma'am, is it based on the Gibbs energy?
Kept phone and wind. Where are you, Anand? Sleeping?
Ma'am? Ma'am?
Pankaj?
Ma'am, Chinmaya is trying to say the answer, ma'am.
Isha wants to say.
No, ma'am, Chinmaya is telling me the answer that time. Are you able to hear her, ma'am?
I can hear. Say.
Ma'am, it's me, Chinmaya. Can you hear me?
Yes.
Ma'am, is it based on the Gibbs energy?
Yes, correct. What is it?
Ma'am, the Gibbs energy of Cu2O is higher than that of CO.
Higher than?
That of CuO.
That of? I explained that. Nobody remembers. You are not learning daily notes. So somewhat, it is like the Gibbs free energy of formation of Cu2O. In the Ellingham diagram, we learned there is Cu2O, Gibbs energy of formation is more negative. Less negative. It was on top, isn't it? So it was less negative. And so all the reducing agents could reduce. But whereas when you take Cu2S, the Ellingham diagram will change. It is Cu2S. For sulfides, Ellingham diagram we have to see. What will Ellingham diagram given in the book is for oxides. Now when we see for sulfides, this delta G naught formation of Cu2S will be more negative. That means the curve will be down. Have you understood? So the reducing agents will be up. They are having less negative delta G naught formation. That is why. So Prashant is almost correct. So we cannot use, see, suppose I use carbon and the Ellingham diagram will change because sulfide. So carbon will form carbon disulfide instead of carbon monoxide or carbon dioxide, isn't it? It will form carbon disulfide because we are taking the sulfide graph, Ellingham diagram with the sulfide. So what happens? Cu2S diagram, Cu2S forming from copper because it is a sulfide diagram. That graph will be down. That means the Cu2S, delta G naught formation of Cu2S is more negative. Now understood? So we cannot use. Clear?
Yes, ma'am.
And Anand and all kept phone and went. Pankaj, you are also doing the same thing or answer me. Not at all there. Keeping the phone and going. Pankaj is there. Okay, Anand is not there. Where is Anand? But attendance full is there. Anand, I will catch you. I know that. Arbas is there. Anand, where? Why are you not answering? Now you came. You were sleeping. I was asking you quite a long back. Arbaz is there. Anand, you kept and went, kept the phone and went. Then switch on the microphone. Why didn't you answer? Now only you are answering. Now only you are here. Not sleeping, but you were not present in the class, isn't it? So, I know that. I will catch you. See, 1 year I taught you, na? I know who all are doing the what. So don't do that. You didn't hear the question also. We were doing, isn't it? So you were doing 6.3. So, I know that. I will catch you. Okay, I know every one of you. So don't do that. Okay, so 6.3, answer you right. It is difficult to get copper from copper. It is difficult to get copper directly from copper sulfide. Copper pyrite. It is difficult to get copper directly from copper pyrite. By reduction. Copper from copper pyrite by reduction. Next sentence. Copper pyrite is a sulfide ore. Copper pyrite is a sulfide ore. What is the formula of copper pyrite? Bracket you can write CuFeS2. CuFeS2. It is a sulfide ore. Now, which one, Agnel? Second sentence?
This answer.
First sentence, it is difficult to get copper directly from, it is difficult to get copper directly from copper pyrite by reduction. By reduction. Second sentence, copper pyrite, bracket, CuFeS2 is a sulfide ore. Written.
Yes, ma'am.
Next sentence. Delta G naught formation. Delta G naught formation. Delta G naught F you will put it down. Delta G naught F of Cu2S. Delta G naught F of Cu2S from copper is more negative. From copper is more negative than those of carbon disulfide, CS2 from carbon, than those of
Can you repeat this line?
CS2, carbon disulfide, than those of CS2, carbon disulfide from carbon disulfide, CS2 from carbon, and H2S, hydrogen sulfide, H2S from hydrogen. That is enough. You understood the reason? So the curve will be, which one? Last one. Last sentence is delta G naught F of Cu2S, delta G naught F of Cu2S from copper is more negative than those of CS2, that is carbon disulfide from carbon, and H2S, hydrogen sulfide from hydrogen. Done?
Ma'am, could you please repeat?
What Kirtana is asking?
Ma'am, she is asking to repeat.
Yo, this is the fourth time I am repeating. Which one repeat? Why are you not writing when I say? Which sentence?
Ma'am, last line, ma'am. Last.
This time you should write delta G naught for F. That sentence. Delta G naught F of
Yes, ma'am.
Cu2S from copper is more negative than those of CS2. CS is for sulfur. CS2 from carbon and H2S from hydrogen. Written now?
Yes, ma'am. Actually, voice was breaking.
How others are writing? You just see the record and then write. You are not able to hear me. Others have written.
Now.
Have you written, children? Answer now.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
So you can hear my
Yes,
voice, others?
ma'am.
Yes, ma'am. Clearly.
Okay. What? So the next sentence, one more sentence you write. Therefore, carbon and hydrogen cannot be used. carbon and hydrogen. Carbon and hydrogen cannot be used. Carbon and hydrogen cannot be used to reduce. Carbon and hydrogen cannot be used to reduce Cu2S to Cu. Cannot be used to reduce Cu2S to Cu. Clear? Have you understood? So delta G naught negative means copper to copper sulfide curve will be down and reducing agent will be up. So they cannot reduce, isn't it? Okay. Clear? Next question we will, any doubt? Next questions, common elements present yesterday, anode mud. I told you to learn, isn't it? Titanium, selenium, tellurium, gold, platinum, silver. So that we have already done. And next one, direct question. Next one also direct. Role of silica in the metallurgy of copper. Silica acts as a flux. You write the reaction also. Okay, it is there in the extraction. And chromatography, direct question, criteria we already did. We have done most of them. Refining of nickel, Mons process we have done. And separate alumina from silica in the bauxite ore. So that is leaching, isn't it? Giving examples, roasting, calcination we have done. Cast iron and pig iron difference we have done. Differentiate between minerals and ores we have done. Why copper matte is put in silica lined converter? Tell me. 6.17. Why copper matte is put in silica lined converter?
And to remove the FeO
It is
form.
used to remove the slag.
Now, to what Anand is saying?
Remove FeO formed.
Yes, to remove the impurity, isn't it? So that part you will write yourself. Silica lined Bessemer converter, because silica in that case is a flux, isn't it? So why we are putting it in silica lined Bessemer converter? To remove the impurity. FeS will be converted to FeO and that will form slag. That you have to write. You will write yourself, it is in the extraction, isn't it?
Yes.
To form the slag, correct, Prashant. FeSiO3. So that you write. And what is the role of cryolite? Yesterday we learned in aluminium extraction it is there.
Increasing the melting.
And leaching low grade copper ore yesterday we learned. And then the remaining questions. 6.24 chlorine as byproduct. Yesterday I gave you the notes. Isn't it? Role of graphite rod in the metallurgy of aluminium. Tell me. That also in the book I told you to underline. What is the role of graphite rod?
Ma'am, it is used in the anode, ma'am.
Very good. That only. Okay. It is used as anode and you have to say oxygen liberates at the anode. About graphite rod, we underlined and so that part, oxygen liberates at the anode will react with the carbon to form carbon monoxide and carbon dioxide. That byproducts are gases. The products are gases that will go off. Isn't it?
You also add coke powder over the electrodes, right? To prevent this. You also add coke powder over the electrodes.
To prevent?
To prevent the loss of the electrodes.
No. So there are different ways. We have to replace the anode because it will get used up, na? So no, sometimes what we do when it gets exhausted or then you replace. So you must have read somewhere putting coke powder so that carbon only, na? That will react with oxygen. That is the reason. Because it is reacting with carbon, the oxygen produced. Isn't it?
Yes, no, and loss of electrode is prevented.
Okay. So that is it. Remaining questions, we have all 6.27 also we have done. Under what condition? You remember the temperature? Can anybody fast tell me at what condition aluminium might be expected to reduce magnesium oxide? Under what condition aluminium is expected to reduce magnesium oxide? Anybody remembers? See, you have to learn, children.
Ma'am, above 1000.
Ma'am, above high
Good,
temperature.
Temperature.
Priyanka. Above 1,350 Kelvin, isn't it? Not 6,000. 1,000 for aluminium, magnesium, the temperature is 1,350, isn't it? Okay, with the temperature you should learn. And then, so that chapter is over. And we will now go to the next chapter, P block elements. This is a difficult chapter. Difficult because you don't have the habit of learning the same day. If you do not do that, normally I was waiting for the classroom. I take this chapter in the classroom and I make you learn the equations along with me. But now this is, I cannot see you. And you are smartly saying that the too much of data consumption, all that stories. And no, you are not even switching on the mic. So, but still I know you. No? I know you very well. I will catch you if you do something. Okay. So what I will do, so I will try to make you, because here this chapter is the chapter where you are finding maximum equations, and so equation based chapter, and that is the difficulty. And there are, see, in this chapter there are 3 types of questions. Every question paper, every board question paper you will see. This chapter consists of 3 types of question. One is equations, and second one is give reason, and the third one is structure. They will ask you to draw the structures of compounds. Out of that, structure is comparatively easy. Give reason also, there are so many give reason questions. So you have to concentrate equally on these 3 topics. Equations, give reason, that you should understand, and you should understand that the maximum mark from all the chapter, the maximum mark is coming from P block elements. Okay, so that is the reason this chapter is very important. And this chapter, if you do not learn every day, you just cannot learn this chapter. If you are thinking we will sit and learn, it will not happen. You can ask your seniors. The most difficult, those who learn regularly, for them it is very easy. Okay, so that now we don't know till when the lockdown period, so I have to take, so I am taking this chapter for 2 reasons. One reason is, suppose you are getting a break, which I think you may be getting a break in June, I don't know what is the decision. So then you can practice. This is a difficult chapter. Once you have done P block thoroughly, I think 1/3 of your difficulty is gone. It is that important and that difficult. All of you understood? And so this much only I can tell you. Remaining, if you understand the seriousness, you will learn every day. Every day if you learn, this is very easy. Okay? Have you understood? This chapter take very seriously. Will you do every day? And to some percentage, I will make you learn the equations in the class, because some hints, this is because in equations, children, you have to learn by heart certain things, and this is not organic. Organic, once you have a grip, then you can guess. Here guessing and all not there, most cases. Guessing, some cases you can guess the byproduct. There are difference between organic reactions and inorganic reactions. The first difference is, if you do not balance the equation, it is, you in inorganic, you have to write all the products, means byproduct and balancing. If you do not balance, then you will lose mark. If you do not write all the products, you don't get any mark. So that is the difficulty. Unlike in organic, most of the reactions, I tell you, above the arrow we put and then the main product we write, isn't it? So, and balancing then not required. So that makes this inorganic equations difficult. Okay, so you have to balance. So some tips, somewhere I will tell you to learn some reactions. I will tell you to learn the numbers. Like you remember gold and silver, I said, you learn 4m plus 8cn minus plus 2h2o plus O2. I told you, na. So that once you learn not many reactions, very few, then that number will be in your head. So that way I will make you learn. Take a rough book and practice. When I say learn, don't look here and there, learn. That will help you a lot. And so you can ask your seniors, P block elements, those who are sincere and listen to me, they don't have any problem. They learn in the class itself. Take 10 or 15 minutes every day and practice. And be very thorough with the equations you learn that day. And then another hint is that once you learn the equation, see now the time is very less, 1 hour. I don't take much of equations, so you have to recollect the equations and don't laugh and ignore it. That is the way to learn equations. Means you learn in the class itself. I will try to make you learn. After that you will practice at home, even though you know that I know that, because after 5 minutes you may forget. So you have to recollect this reaction we learned today. 10 reactions. Which are the reactions and what are the reactants? What are the products? Any conditions are there? Like that you have to tell yourself. And then sometimes you will be able to recollect. Sometimes you don't. If you do not recollect, then see the book. And after some time again. And after another subject again, think what I learned. Difficult topics, by recollection, you will be able to remember. And you will be able to see that page in your mind when you write the exam. Have you understood? Okay, so we will start with the P block elements. Here again, they have, see last year, the group 15, that group 15, nitrogen family, that group 15, so many equations are there, so many compounds of nitrogen and phosphorus. That was taken out last year, and last to last year, these two, the group 15 elements were not there. Okay, so a major part of P block group 15, they did not learn. This year, the final syllabus hasn't come, but then the syllabus which came before the, after the lockdown also, they said they reduced, and the syllabus which came, they included group 15 and solid state. Okay, so for time being, I am not taking group 15. We will wait. The government is saying that they are reducing, but then 2 days back another circular came in which they are saying they will not reduce chapters from 9 to 12. So maybe some extra sentences given that they may delete, not the topics, like that they are saying. So anyway, for time being, I am not taking group 15. When the syllabus comes, then it is there, later we will take. Is that okay?
Yes, ma'am.
So now we have in your syllabus, you have group 16, 17 and 18. Okay, group 16 is oxygen family, and group 17 halogens, and group 18 noble gases. Okay, out of that you can say every year group 18 one question will be there. Group 18 is the most important. And so every year what I do, I take group 18 first, because 16 and 17 also many equations are there. By the time you reach, you are tired of equations. So I don't want that. So group 18 equations are comparatively easy and the most important equations. All the equations they can ask, but then from group 18, one question, every question paper you will see. And the equations are not very difficult. So I will start with the group 18, then we will start from the beginning, 16 and 17. Understood? So the group 16, group 18, I am starting. Okay, and you have to notes, not much of notes, equations are there, but then you have to sit there with a rough book. Are you all having a rough book? Because you are going to learn equations along with me. Is that okay? Are you having rough book with you? Yes, Abhishek. Good, Abhishek. So we will start. So the questions which comes also, I will tell you. Okay. So the first thing is about, I told you, there are three types of questions: give reason, structure, and equation. So it is not only equations. So the first point, that the any group, the electronic configuration, that group 18 inert gases. Group 18 inert gases. The noble gas we say because they have 8 electrons in their outermost shell. All of you know that, isn't it? So they have NS2 NP6 configuration. All the outermost shell is filled, S and P. They are filled. That is why they are called inert gases, because they have 8 electrons in their outermost shell, so they do not react. That story all of you know, isn't it? So we will take the chapter and take the page. I will tell you to mark. So, electronic configuration, you know that electronic configuration, the general electronic configuration, all are having NS2, NP6 except helium, isn't it? Helium, NS2, no p orbital, that you know. And so they are having NS2, NP6. Clear? Now, atomic size, that is the electronic ionization enthalpy. Ionization enthalpy will be very high because completely filled orbitals. So it is difficult to take any electrons, isn't it? Stable electronic configuration. This all of you know. So ionization enthalpy will be very high. And one point is there, children. Ionization enthalpy, if you compare, which are the members of group 18? Helium, neon, argon, krypton, xenon, and radon, isn't it? Helium, neon, argon, krypton, xenon, and radon. Out of that, the last one, radon, is radioactive. And so we don't find, we don't see that because that reactions are completely different, nuclear reactions, not like chemical reactions, isn't it? So what we okay, so the ionization enthalpy, as we go down the group, it increases or decreases?
Decreases.
Decreases, ma'am.
Yeah, it decreases. So that is the reason the compounds of noble gases, we find only xenon, because xenon, the ionization energy is lowest for xenon. That is the question. You can write one sentence. That is one give reason. Why are we finding only xenon compounds? What is the reason, children? Two reasons you have to say. Size is more. Ionization enthalpy of xenon is less. That is the first give reason question. Okay, so we don't find any other noble gases, compounds. Compounds, it is difficult to form because they have completely filled orbitals. Have you written why only xenon compounds are known?
Ma'am, can you repeat the
Why
question?
only xenon forms compounds? Why only xenon forms compounds, or only xenon compounds are known? Got the question?
Yes, ma'am.
Answer. Naomi wrote the question. Answer. Xenon is having the lowest ionization enthalpy because xenon is having the lowest ionization enthalpy because xenon is having the lowest ionization enthalpy because of larger size. Because of larger size. Okay. So then they are saying that in the next page, krypton KrF2, one compound is known, but otherwise xenon compounds.
So, ma'am, one doubt.
Krypton also one compound is known.
Ma'am, you told ma'am the ionization enthalpy decreases down the group as the atomic size increases, right, ma'am?
Size increases, yes.
Yeah. So why doesn't radon form compounds?
Radon is radioactive. I told you, na, that reactions are not chemical reactions. They are nuclear reactions.
Okay.
It is entirely different. So we don't put that radioactive compounds with this.
Fine, not fine. Got it.
Okay. So
Okay.
written. So that is the first give reason question. Then atomic radii, you know that it increases down the group. Then comes electron gain enthalpy. So one point is there, children. See the previous question. Electron gain enthalpy, they have 8 electrons in their outermost shell. So they do not accept also any other electron. So last year we learned about electron gain enthalpy. It is that if they do not accept electrons, then electron gain enthalpy will be positive, more positive. We learned, isn't it? If the electron gain enthalpy more negative means it easily accepts electrons. You remember that?
Yes, ma'am.
Last year. So you can add one more point there in the previous question. It is having less ionization enthalpy and more positive. So less ionization enthalpy and less positive electron gain enthalpy. That also correct, isn't it? Less positive electron gain enthalpy. Okay. Then physical properties. Physical properties, they are all having, it is answer is given in the box. So I am not saying noble gases have very low boiling point. See, first point, they have given the answer. I will explain. Noble gases are monoatomic. Helium, He, neon, Ne. We don't say Ne2, He2. They are monoatomic, isn't it? And so they since they are monoatomic, the force of attraction between the atoms, that is very less. Since they are monoatomic, there will be interatomic force of attraction, that is very less, and only van der Waals, weak van der Waals forces are there. So they can be, it is very easy to break the interatomic force of attraction. So boiling point is less. Answer is given there in the book. Have you understood? You have to say that they are monoatomic and interatomic force of attraction is only weak van der Waals force. So it is easy to break those forces, and so boiling point is very low. Okay. And helium is having the lowest boiling point, 4.2 Kelvin. It is very less, isn't it? Not much lesser than the room temperature. So helium is having the lowest boiling point, 4.2 Kelvin.
Could you please tell where it is in the book so that I can just underline?
No, it is full. You have to learn. Noble gases being monoatomic have no interatomic forces except weak forces, and they can be easily liquefied. That full is their answer. You can say in simple sentence. Okay?
Yes, ma'am.
It is in the box, Naomi.
Yeah, I got it.
So here, next question is, see, helium is having the lowest boiling point, 4.2 Kelvin. Okay, so helium is used for cryogenic experiments. Cryogenic means experiments conducted at a very low temperature. Okay, so that point you can connect with the uses of helium. In the last, it is liquid helium finds use as a cryogenic agent for carrying out various experiments at a low temperature. This question comes in 1 mark, and you should be knowing. One use of helium. It is used in cryogenic experiments. Can be the same question can be asked as 1 mark question for give reason, and for which element is multiple choice. They can ask which element is used in cryogenic experiments. Underline that point. Helium is used. If it is asked to give reason why helium is used in cryogenic experiments, what is the answer? It is having the lowest boiling point, 4.2 Kelvin. Understood? Okay, we can move ahead.
Yes, ma'am.
Okay, so these are the questions. And then another one is that, one more sentence. It has an unusual property of diffusing through most commonly used laboratory materials like rubber, glass, or plastics. That also, these are all informations we get. Helium has that unusual property. Okay. Now coming to another one, how the discovery. Earlier, it was believed that since they have inert gas configuration, they will not react, and we cannot prepare any compounds of inert gases. Okay. So then the scientist Neil Bartlett, what he did, he prepared a red colored compound, O2 plus PTF6 minus. That was a red colored complex he prepared in the lab. Then he suddenly noticed that ionization enthalpy of oxygen and xenon. Ionization enthalpies of oxygen and xenon are almost the same. Oxygen is 1175 kilojoules per mole and xenon is 1170 kilojoules per mole. That way he then thought, why can't we prepare, since ionization enthalpy of oxygen, molecular oxygen and xenon are the same, why can't we prepare? So he prepared a compound with oxygen, O2 plus PTF6 minus. So what he did, he tried a compound with xenon instead of O2, xenon and PTF6 minus. So he got a compound which is Xe plus PTF6 minus, which is also a red colored compound. So that is how he started preparing the inert gas compounds. So in fact, xenon compounds. So here 2 questions are there. Have you understood what I said? So the first question, what led the scientist Neil Bartlett to discover xenon compounds? That is the first question. Okay, and the answer is, what led him? He prepared a compound, a red colored compound of oxygen, O2 plus PTF6 minus. I will mark in the book, you don't need not write. And then he noticed that ionization enthalpy of oxygen and xenon are nearly the same. So he prepared. Okay, clear? So you mark in the book. I will read that. So the scientist Neil Bartlett observed the reaction of, underline that, observed the reaction of noble gas. So you can leave that. He prepared a red compound, O2 plus PTF6 minus. You can write in xenon. See, chemical properties you take, Prashant. It is group 18, last pages. Okay. Take that and underline the sentence. I will read once again. Underline the scientist's name, Neil Bartlett. That, and then come to the next sentence. Neil Bartlett prepared a red compound, O2 plus PTF6 minus. Same sentence is not required. You can simplify. So he prepared a red compound, O2 plus PTF6 minus. He realized that the first ionization enthalpy of molecular oxygen, 1175 kilojoules per mole, was almost identical with that of xenon. 1170 kilojoules per mole. So he prepared a compound of xenon Xe plus. So he prepared a compound of xenon Xe plus PtF6 minus by mixing PtF6 with the xenon. That is the reason. That led him to make more xenon compounds. Understood? Got, children?
Yes, ma'am.
Second question. I will write on the board the second question which came. This you can write. This was the question came. So if you do not write this, you will not, and if you do not read this introduction, you will not get the answer, isn't it? The answer is very easy. So answer is Xe plus PtF6 minus. That's it. Okay, understood? Written, children. So 2 questions from there. Okay. So we'll continue. Clear this much? So how many questions we have seen? Done? Okay. So now xenon compounds. We are coming to xenon compounds. Not much of equations, but to give reason, everything learn and keep. It is very important daily learning. Okay. Now coming to xenon compounds, you have 3 xenon fluorides. XeF2, XeF4 and XeF6. Methods of preparation. The first method they have given is direct combination with the xenon, fluorine in different proportions, and the conditions. See, XeF2, you have to learn like this. XeF2, Xe plus F2 giving XeF2. Equation is so easy, isn't it? But the conditions are there. 673 Kelvin, 1 bar pressure. Okay. Second one, I don't have to write also. Equation is Xe plus 2F2 giving XeF4, right? Easy, isn't it? 2F2 is required for XeF4. But the conditions, that is the only thing. Since equation is very simple. Condition 673 Kelvin becomes 873 Kelvin and 1 bar becomes 7 bar. Done? Now the third one, XeF6. Xe plus 3F2. Then only F6 will come, isn't it? Xe plus 3F2. And the temperature you see from 673 to 873 again reduced to 573 Kelvin, but the pressure is increased to 60 to 70 atmosphere. So 3 equations. Have you learned? You have to learn like story. See, once more I will say Xe plus F2 giving XeF2, temperature 673 Kelvin, 1 bar pressure. Xe plus 2F2 giving XeF4, temperature 873 Kelvin, 7 bar. And the next one, Xe plus 3F2 giving XeF6, temperature 573 Kelvin, but pressure is high, 60 to 70 bar. Clear?
Is the bond here covalent or ionic?
They are all covalent compounds. Okay. Now, so this you have to learn all the equations. This is not much asked. The question which asked in the preparation I am going to write. You can get XeF6 from XeF4. So the question asked I am going to write on the board. So equation is very simple. This is the question. They will say complete the equation. Equation XCF6 plus O2 143 Kelvin. Okay, 143 Kelvin. Done?
Yes, ma'am.
So this is how they are asking questions. Okay, they do not ask you like write the method of preparation. May not ask. Okay, so now there are two types of reactions. That's it. One is hydrolysis. This year also they asked hydrolysis of XCF2, XCF4 and XCF6. That is one type of reaction. The second type of reaction is, see the xenon fluoride, they donate fluorine and they accept fluorine. In some cases they donate fluorine, in some cases they accept fluorine. Okay, so these two reactions are there. I think I will take those reactions and hydrolysis together we will take tomorrow. Okay, so the fluorine donors and fluorine acceptors. See, you just have to remember when the xenon fluorides react with alkali metal fluorides. They have given in the book as MF. M is an alkali metal which can be sodium, potassium, rubidium, cesium, not lithium. Okay, so with alkali metal fluorides, it will take fluorine. That reaction I will write first. Okay, have you understood? So I will write that first. So this is given in the book. They will ask you only the equations given in the book. MF. So M can be, I said, sodium, potassium, rubidium or cesium. So this will take. So the cation will be M plus, anion will be XCF7. It took the fluorine minus. So you will get a cationic and anionic species of xenon. Have you understood?
Yes, ma'am.
And the question is you first learn this by heart. I said you have to learn in the class. Okay, so here you should be in your mind. M is an alkali metal and it will take fluorine from alkali metal. So we normally write cations first, NaCl, Na plus Cl minus. Cation should be written first. So we are writing M plus and the anion, it took fluorine. So XCF7 minus. Have you learned? Write 2-3 times and learn.
Ma'am.
Okay, so now the question I will write. This is not the question again. This is the question. Complete the equation. Can you complete? They will give any one alkali metal. And complete all of you, then check with the board.
Done, ma'am.
Got it? How many got the answer? So easy,
Got it, ma'am.
isn't it?
Yes, ma'am.
So they accepted fluorine. Now we will write with the donating fluorine. Okay? Clear?
Yes, ma'am.
Ma'am.
So now donating fluorine. There we will take XCF2 and XCF2.
Ma'am, Anant is asking something.
Who is asking?
Ma'am.
Anant, ma'am.
Yes.
Am I audible?
Say.
Only XeF6 or XeF4, XeF2 can also react.
Nah, they can react. But then why I wrote that? Na? It is completely textual. Na? They will ask with the textbook only. Otherwise, if they ask also, you should know that it is a proton acceptor. So if it is XeF4, in case they ask XeF4, then you know that it will become, suppose, since Anand is asking the question, I will write. He is asking, is it possible with the XeF2, isn't it? KF. If at all they ask, you can write now. K plus XeF3 minus. Got it? Got it, Anand?
Yes, ma'am.
You can write. It is possible.
Got it,
So
ma'am.
you know that it will accept. It will donate, isn't it? So it is, this one will donate. So you write to the, understood?
Yes, ma'am.
Okay, now coming to this. Same reactions I am writing. So this will take. So if it takes means XeF becomes plus, and this one is taking BF6 minus. Clear? And here also it is taking one fluorine only will be taken plus SbF6 minus. Any doubt you can ask. Reactions you will write now itself and learn. You just have to remember. What, Naomi? Here, this will give fluorine, one fluorine to PF5. So if one fluorine goes means XeF2, one went over there, plus. And that fluorine went here. So it becomes PF6. It is getting fluorine, so minus. Clear? And similarly here, one fluorine went over there. So it becomes XeF3 plus. That fluorine came here, SbF6 minus. Now clear?
Excuse me, ma'am. Ma'am, this is for donating.
Say Priyanka.
Ma'am, this is for donating. Is this for donating or
the xenon fluoride is giving? It is one case. In the previous case, it was taking, accepting. Now XeF2 is giving one fluorine, so it becomes XeF plus, and other one is taking. So it is PF6 minus, isn't it?
Yes, ma'am.
Clear, children?
Got it, ma'am.
Got it? And then practice, and we will. The xenon compounds will give. The xenon fluorides only will react. Is that okay, Prashant? And practice, and so. No, Prashant, what are you saying? To which compounds? See, PF5 and SbF5. The two compounds are there, na? So in this case, xenon will give. Okay? So then bye for today. Learn and come tomorrow.